Welcome everybody to the next steps in vehicle electrification technician preparation. This is the fifth and last section that we are doing on certifications, vehicle electrification certification. This one's titled Introduction of the Society of Automotive Engineers Fuel Cell System Certification. We are grateful to the folks, Maddie, and thank you for the music and the coordination. We want to thank our friend Janet and Brian for being our sponsors through all of this. So we have Green Transportation Summit and Expo. We have the West Coast Collaborative and Mobilize California that have been helping and putting this together. Thank you all. Next slide. I want to mention that the Green Transportation Summit and Expo is taking place in Tacoma, August 16th through the 18th. And you can find out more about the event at the GTS Summit, expo.com. You can see the website right there. And Maddie, who's online right now, is a point of contact as well. I want to thank Green Transportation and those who help organize this. It's a major event. I also want to express thanks to the Society of Automotive Engineers Vehicle Electrification Committee, who are reviewing the standards right now as we are going through this process of certification. A lot of folks, a lot of involvement, a lot of direction setting. Thanks again. Our sponsors are Western Washington Clean Cities, Advanced Vehicle Training Group Northwest, National Science Foundation. Then we have the Clean Cities of the Columbia-Willamette, Future Tech, East Bay Clean Cities Coalition, and the ATL. Thank you all. Housekeeping. Let's go over a few housekeeping things and then we'll get rolling. So if you want to chat with other attendees, go ahead and use the chat box. If you have questions, make sure you use the Q&A box. Feel free to log in your questions during the presentation. We'll answer those first. You can make comments. We may not comment on the comments, but if you have a question, we'd like to address that. The webinar recording and slide deck will be available to all attendees. So we plan on sending this out to everybody who's attending. I have some other folks who are advisory that will also receive that, or if anybody else would like to have the recording, make sure you see me, Ken Mays, and I will get that to you. Next slide. Our speakers today, and I'll introduce myself. I'm Ken Mays from Central Oregon Community College. I've been the principal investigator on the NEVTEX grant, along with John Fralla, who's our first speaker, actually. And John is the lead professor at Rio Hondo College down in Whittier, California. We'll have Tim Perzanowski, and he's working right now and lots of things as a NEVTEX consultant. And he also is partnered with Mark Horton, Dr. Horton, who's the Chief Technology Officer for Future Tech Auto, and many more things on that. And Mark will be summarizing and drawing us to a close today. Next slide. It's my privilege to introduce my partner in the NEVTEX grant, National Science Foundation grant, John Fralla. And John coordinates the Alternative Fuels program at Rio Hondo College. He's the co-principal investigator for the NEVTEX National Science Foundation grant. He's an Associate of Science, Advanced Alternative Fuels Transportation, and he's Associate of Science, Electric and Fuel Cell Vehicle Technology. Those are 2 degrees that are offered at Rio Hondo. He offers a Certificate of Achievement in Tesla Technology and Volvo Lights Project at Rio Hondo, the electric Class 8 trucks. And just recently, Rivian Electric Vehicles has partnered with Rio Hondo College, and John Fralla is a major part of all of that. And welcome and congratulations, John, for the incredible amount of things that have been going on in Southern California.
Thanks, Ken. I appreciate that. Hold on 1 second. There it goes. It's set up here, hold it. My technical difficulties on my end. Okay, Ken's kind of gone over some of the stuff we do at Rio Hondo. The program's 25 to 28 years old, depending on where you look at the calendar. Right now, we've got some of the very large components of the electric and fuel cell program there, where we are now placing students in the fuel cell industry. That pops a little slow there. So the grant came about when Ken and I were back in the early NSF days. I had a grant for electric car vehicles technicians, and Ken had a grant for hybrid technicians. And we had met. After our grants had finished, Ken had approached me and said that he wanted to do these training standards that we had talked about. So between myself and Ken, we kind of brainstormed and put this together and did some research and found out there was no uniform standards for technicians who are working with high voltage or high pressure fuel systems. Through SAE or through CSA or through any of the federal or state bodies, there was nothing in a uniform standards. So we went and looked for the existing training formats that are out there. We found a few of them, but they were mainly OEM and they were not transferable to the public or to different types of transportation entities. So we would approach ourselves and we wrote the grant, and it was funded through the National Science Foundation. And we started putting these standards together, reaching out to the industry, because we figured if the industry would back us up on it, we might have a good shot at getting these things put into a national format for training. So we approached the Society of Automotive Engineers and looked at what they had. Dr. Mark Horton was a real help in getting us the contact information to that. OSHA, we had talked to them about it because there's nothing in the OSHA standards in the transportation side for electronics yet. Department of Transportation, Department of Energy, California Energy Commission was a great help for us in the state of California, getting us in touch with people who are requesting these types of areas for some kind of certification or training. So we contacted the CSA and found that they had just changed their format. They no longer had a manager in place for compressed gases. So they were not at that point of time intending to create or establish any training for hydrogen gas, which is at a much higher pressure. National Fire Protection Agency had NFPA2, and at that time I was asked to join them on the J2990 committee. So I've been on that committee for 6 years now, along with Jennifer Hamilton and the other group there, trying to establish standards through NFPA, but nothing was set in there for technicians. So we went to the industry, and this is where Hoke and Sycor and then Swagelok, who make the fittings and the tubing, came back and said, we have our industry-owned certification, but nothing that applies to a technician who's working on a vehicle or transit or heavy-duty truck. So we went into the meetings with the different look at the standards. So out of this whole process, which took us a little over a year to really figure out, we figured out we needed to establish the need for that tank inspection because there is nothing out there. Hydrogen tanks are a lot different than natural gas or propane tanks. Hydrogen fuel is cryogenic, so we have to look at an embrittlement factor on the tanks, the fittings, and the controls that go along with it that we don't have to in CNG. Establish the need for that high pressure piping or tubing certification because it is different and it works at very low pressures and temperatures. Works high pressures and low temperatures. And then establish the need for technician high voltage certificate training of some kind. The transit industry and the truck industry all came back and said, we would like to take something we can come back in and get our employees trained that we know they're not going to get hurt while they're working on this new type of product that they're just now getting. And then we wanted to establish some kind of uniform standard that could be used all the way across the United States and possibly into European standards also. And this is my quick drawing here of what happens if you're the ground and not the circuit. This is what we tried to avoid on it. So the project, as it came together, it helped us build relationships with really essential advisory partners, as Ken had talked about earlier on the opening. And this is partners throughout the country. We had UPS, we had FedEx, we had New Flyer, Gillig, Cummings, Ballard, and a lot of the other cell manufacturers. Eldorado Bus came in on this because they're building a fuel cell bus now. So all these people came together, and it helped us establish these connections with them so that we could ask them, how is this bus put together? What kind of products put together with it? What kind of safety is the manufacturer of these parts asking to come along with their training? And we took all that training, put it together, and this is how a simple template of this, or sample template of this, came together. And we started creating the advanced standards category that's established as we plan for the refinement of the standards and criteria. In the previous lectures here, in the first 4, you guys learned a lot about high voltage electric standards, high voltage for the electric chassis. And now we're creating this same type of training to be applied to the hydrogen fuel cell side of this, because it's a similar type of format, but it's different, mainly because the fuel is stored between 5 and 10,000 PSI. It is not stored at a low pressure. It's very high pressure. So that means that the type 3 and type 4 tanks have to withstand a lot more pressure in a colder climate than the CNG does. So the standards were different. The grant also helped open the door for us in California when we established a Volvo Lights training project with AQMD and California Air Resources Board on a full electric Class 8 single and dual axle semi, which is in production right now. It was 50, there was 5 trucks on a pilot that was out last year. They all have proved it. The truckers going from San Pedro up into the Riverside area where the transit area is for the rail. So they're taking the shipping containers from Long Beach and LA, taking them out to the rail yards and doing these returns on a single charge on a Class 8 electric semi. The trucks didn't have any issues with it. There were no major breakdowns. And so now DHE, NFI, Velocity have all started purchasing these vehicles. And then now we've got UPS, which has purchased a few of them. And then you have companies like Anheuser-Busch, which is also buying the Class 6 trucks for their beer delivery here in California. So we're seeing more involvement of the electric vehicles come into a bigger format. So this is where the standards came in to be even more crucial, because passenger cars is a selected group of people that do these repairs. When we get into Class 6 and Class 8 electric trucks, this goes into a specialized yard where the service is done. And these guys, this is all new to them. They don't have anything to do with voltages from the 480 to 680 volts. The new Tesla semi is 1,000 volts, operates on 600 volt background. So these are very high voltages that not in the trucking industry we've seen in a long time. So this took a different type of training to be developed. Also with a fuel cell on the transit side, and now the semi Freightliner has it, and also the Daimler Mercedes has a fuel cell truck and a Class 6 also. So we're seeing these trucks come into another market. Again, technicians have not seen this or been exposed to it before. So these standards that we've developed are currently being finalized through the SAE ITC certification process. Level 1 and level 2 standards, as we'll talk about, have already gone through the vetting, and level 1 class is coming up very quickly. And then level 2 is coming up right after that. And then level 3 is being finalized right now by the SAE ITC, and that will be delivered right now. It is going to be delivered at Sunline Transit in Palm Desert. That's what our scheduling is for right now. So this year, we'll be able to offer all 3 levels of 1, 2, and 3 dealing with a hydrogen fuel cell. And if you need any more information or contact on the fuel cell stuff or the standards, Ken and myself, both of our information is right on here. You can get a hold of us, and if we can't answer the question, I'm sure we can get you to someone that can. If you're interested in any of the training or hosting training at a college, this is something that you can get a hold of us, and we can direct you to the person that can help you with that.
Thank you, John. And I just want to make a short correction there. The level 1, level 2, and level 3 are for vehicle electrification. Level 1 will apply to fuel cell, but we are drawing out the following fuel cell certifications. Not quite ready for those yet, but just wanted to clarify that if that's okay.
Thank you much.
What the fuel cell training programs, not very many of those in the country. I don't know about Canada, but what do we have going right now in our nation for fuel cell training programs?
Well, Rio Hondo's been in the forefront of a lot of this in California because of the amount of hydrogen we have in California. We are on 41 stations, headed for 49 by October, November area in the state. But we've got three large uh, plants that have been put in place. One of them at Sunline Transit in Palm Desert. That one right now is the largest electrolyzer in the United States for converting water to hydrogen fuel. They received an FTA grant to do this. So we're watching that part of the industry come around very quickly. And as far as training in California, Rio Hondo is the only one that's doing this right now. Stark State in Ohio is doing it also. They have an infrastructure in place. And then also in Michigan, we have some training there at a university level, but that's mainly for stationary fuel cell in a backup mode. So yes, it's limited right now.
John, where are you sending your students? Are you graduates? Are they local? Do they stay local right now when they finish the program for alternative fuels?
Yes, well, our alternative fuels, it takes into consideration all of the high voltage as well as the emerging fuel cell side. So fuel cells, we're watching them go into the transit industry right now because the transit is expanding into fuel cell because we have, in California by 2024, we have a zero emissions policy that's starting to take place with Class 6, Class 8, and transportation on the bus side. So these technicians are getting jobs at LA Metro, Orange County Metro, Norwalk, Glendora, Gardena Metro. A lot of it is transit industry side for those technicians because it's still early stages. The guys that have the electrical experience, they're all over the United States. I actually have two females that are over in England right now that have created or opening up a station there or a service center for Tesla. So we've been able to, through the Tesla program, to graduate about 230 technicians in 5 years. And these students are paid interns through the program, and they are all over anywhere in the United States that they choose. They want to go and start that service center experience with Tesla. We're, as you said earlier, we're starting the process right now with Rivian. We will be the West Coast training facility for them starting July 1st, hoping to have those students at that main service center in Gardena in California, expanding out from there. So the Rivian is taking slower steps, not quite as expanding as quickly and rapidly as Tesla did, but the product will be out there and these will be trained people when the customer or consumer gets the vehicle in their hands.
John, thank you so much for being here today. That was a great presentation, and I'd like to go ahead and move us along.
Okay.
Thank you. Next slide. Next slide. It's my pleasure to introduce Tim Perzanowski, and Tim has been working for the NEVTEX grant as a consultant. He, as you read just a brief portion of his bio, I'll read this. While working for Hughes Aircraft, Delphi, General Motors, and Rivian, Tim has accumulated 40 years of experience in power electronics, 27 years of experience in electric vehicles, and 20 years of fuel cell electric vehicles. During his career, he has been a quality engineer, I'll say that right, manufacturing engineer, process engineer, design engineer, systems engineer, and field service engineer. He spent the last 20 years as a senior project engineer responsible for training, field service, and maintenance of various General Motors fuel cell electric, hybrid, and battery electric prototype vehicles and fleets. He has trained engineers in the US and China, General Motors and dealership technicians, first responders, college students, and the public on operation, diagnosis, and repair of fuel cell electric vehicles, both inside General Motors and under contract with the US Navy. Welcome, Tim, and we're looking forward to this.
Thank you, Ken. Appreciate everybody giving up their part of their Friday. Maddie, first slide, please. So the first slide talks about why fuel cells. Well, fuel cell vehicles are electric vehicles, but rather than deriving their DC current from a battery pack like a BEV, we get it from a fuel cell, usually a PEM fuel cell. And I have a habit of lapsing into what I call TLAs, three-letter acronyms, so I apologize for that in advance. But a PEM is a proton exchange membrane fuel cell. It's just one type of fuel cells that are out there. Fuel cell vehicles are viable, low or zero emission vehicles. They're one of the few out there besides BEVs. One of the main things, they allow the use of excess renewable energy. We use that excess energy to create a transportation fuel that can be stored and transported. One of the major features of that is it allows the time shift of hours, days, or even weeks between when that electric power, renewable electric power is generated and when the vehicle is refueled and uses that power, unlike a BEV, which is basically real time unless you have a battery buffer or some similar mechanism to store that electric power until you need it to charge the vehicle. A fuel cell vehicle is about twice the efficiency of a gasoline engine. A gallon of gasoline and a kilogram of hydrogen are conveniently about the same amount of energy available. The thing is you can burn hydrogen in an internal combustion engine, but it won't be a zero emission vehicle at that point. You run the risk of creating NOx, nitrous oxides, and also any petroleum byproducts that get past the piston rings and into the atmosphere. The only emission from a fuel cell vehicle is water vapor, in addition to air that has been depleted of some oxygen. One of the things about a fuel cell, hydrogen-powered fuel cell, is it allows long-range, hundreds of miles and quick fill-ups in 3 to 5 minutes for an electric vehicle. Next slide, Maddie, please. Okay, there's a lot of similarities between fuel cells and other vehicles, both BEV and ICEs, internal combustion engine vehicles. Electronics and powertrains are very, very similar to battery electrics and strong hybrid vehicles. They're usually actually the same basic designs, but just packaged for better use in fuel cell vehicles. A fuel cell vehicle, most people don't realize, may or may not have a high voltage battery pack. The PEM, one of the features of a PEM fuel cell is quick response time. So in the past, General Motors built vehicles that had either a high voltage battery pack or no battery pack. The limitation is if you do not have a high voltage energy storage system, then you don't get the benefit of regeneration under braking. So you will find that all fuel cell vehicles today have some sort of at least small size high voltage battery pack or ultra caps to store that energy. Compressed gas storage and regulation and metering is very similar to natural gas vehicles. Another thing is they have air machines and compressors, which are very similar to turbochargers and electric superchargers. What we do now on a lot of the vehicles is have something that's very similar to a turbocharger, which is an air machine. And what it takes is the pressurized exhaust air from the fuel cell and captures some of that energy to put back into compressing the air going into the system. Fuel cell vehicles use a lot of similar components, mass flow sensors, temperature and pressure sensors. Heat exchangers and coolant. One of the things about a fuel cell vehicle is that almost all of its waste heat comes out through the radiator. On an internal combustion engine, we get rid of a lot of that waste heat through the exhaust. But the exhaust temperature on a fuel cell vehicle is only in the 100 degrees C range or less. So even though it's twice as efficient as an internal combustion engine, you'll know that the radiators on those vehicles or heat exchangers are much, much larger, which a lot of times will is why the appearance of the front of a like a Mirai or something like that shows so much more frontal area. It actually uses about as much frontal area as like a big diesel pickup or something like that. The ECUs, they're similar to the ECMs and BEV controllers. What you'll find is in most cases, they're standard controllers, but they have a lot more memory. The reason they have more memory is there are more functions and more activities we're doing in a fuel cell vehicle than you would in a BEV vehicle. Next slide, Maddie, please. There are some unique qualities of hydrogen fuel cell vehicles. One is how a fuel cell operates. We'll talk about that in a minute. One is that it keeps generating electricity as long as it has fuel. So this is a benefit, but it also is a Safety concern when you're operating servicing a fuel cell vehicle, because if there's any hydrogen in that fuel cell stack and oxygen is available, it'll keep making electricity. Compressed gas storage of over 700 bar. As John alluded to, these are very high pressure systems for hydrogen. And in actuality, when we refuel a hydrogen powered vehicle, that can go up to 12,500 pounds. The reason for that is compressional heating. So to end up with 700 bars in the tank when you're done refueling, a lot of times you have to get into the 12,000 PSI range to allow for a full fill. Sorry. Hydrogen properties and difficulty in detecting leaks. This is a issue for hydrogen no matter where it's used. We'll discuss that in a minute. Management and removal of water vapor and liquid water. And there are unique vehicle and building codes and standards that we'll touch on briefly in this presentation. Next slide, please. Interesting fact that all the energy we use originated in a star. So anything we're using, basically the majority of that energy came in some way from hydrogen, whether it's light for plants and coal, whether it's uranium that came out of a supernova, whatever the case might be, they all originated in a star. One of the interesting facts going forward is that as we develop fusion power, we're actually bringing that star power to the Earth so that we can generate clean energy for our futures. Next slide, please. One of the properties of hydrogen that's very unique is its buoyancy. So you can see from the chart that it rises 2 times faster than helium and 6 times faster than natural gas. Those of us who live in California will be very familiar with our garages have grates and vents along the bottom edge of the garage. The reason being is the building and fire codes require that is because the fuels we generally use today are heavier than air. So they want those to be able to exhaust from your garage at the ground level. Hydrogen, on the other hand, is going to go straight to the roof. So there are different building standards to allow the escape of hydrogen in garages and other such structures. Next slide, please. Another property of hydrogen is has a larger ratio that it's flammable in, and also the explosive limit. So those require additional safety precautions when working with hydrogen. I always like to say that hydrogen isn't any more or less dangerous than any other fuel. It's just different, and we have to treat it differently. Next slide, please. So this is a picture of 2 vehicles. The one on the right is powered by gasoline. The one on the left was powered by hydrogen, and they created a leak and ignited both fuels. And you can see that the effect of the hydrogen going straight up. The gasoline tends to pull under the vehicle. So there again, it's not any more or less dangerous than a gasoline vehicle. It's just different. A gasoline vehicle is going to be more dangerous if it burns outside a garage. The hydrogen vehicle is going to be more dangerous if it's burning inside a structure. But they're both have their issues, and they both have solutions to solve those problems. What we always tell the first responders that we train is the fact that if you find a hydrogen fire, just leave it burn. It'll be out usually probably before the first responder gets there. But if it is burning when they get there, to leave it burn and just to extinguish anything like maybe tires or asphalt or something else that may be collateral damage from the heat of the fire. Next slide, please. So hydrogen, to emphasize again, is an energy carrier. It's not energy. Gasoline's an energy carrier. Diesel's an energy carrier. The lithium ions, lead acid, and nickel metal hydride and batteries, CNG, they're all energy carriers. Next slide, please. So basic fuel cell operation, the battery's on the left here, and you'll see that the migration of the ions and electrons from one side of a battery to the other, cathode and anode. On a fuel cell, we also have a cathode and anode. The little green balls are the hydrogen going into the system with their electrons. The catalyst allows it to dissociate into hydrogen ions, and those ions are able to transmit across or migrate across the PEM membrane. And when it gets to the other side, it marries up with the oxygen to create water vapor. The electrons, on the other hand, can't migrate across the PEM membrane because of its nature. And so they're forced to go around the PEM cell itself and end up on the other side. And that's how we get our current, our DC current for the fuel cell itself. Next slide, Maddie. Okay, fuel cell components. Throughout this presentation, I use what I call antiques. A lot of the pictures you're seeing are vehicles that were designed in the early 2000s. The reason I do that is because there's been a lot of up integration and combination and elimination and micronization of many of the components. So some of the older components, it's actually easier to visualize what's going on with the parts. So first we have a bipolar plate. And so the reason we call it bipolar is the same plate acts both as an anode and a cathode, depending on which side it is. Then we have a diffusion media that allows the migration of the either oxygen or the hydrogen across the membrane. And as you can, if you look really close, you'll see like grooves. Okay, so those grooves are passages. In the previous slide, you saw sort of grooves where the hydrogen or oxygen would flow up to next to the catalyst and the PEM membrane. What this also does is allow the addition of coolant. So when we form those particular grooves for the gases, we also create a channel inside of it that allows the coolant to flow within the fuel cell to keep it within its operating temperatures. Next slide, please. So this is called a pole curve or polarity curve. As you can see, this is for one cell. So this is one hydrogen cell. And the maximum voltage coming out of one cell is probably 1 volt. And if you try to draw any current out of it all, it's going to drop to about 0.6. So what that tells you is to get the high voltages required to drive electric vehicles, we need multiple cells. So just like in a battery that has maybe 1.2, 1.5 volts per cell, a fuel cell will have 1 to 0.6 volts per cell. So we create what we call a fuel cell stack. So all those components that you saw in the previous slide are sandwiched together in multiples of 200 or 300 to create the high voltage fuel cell stack that we use to drive the vehicle. Next slide, please. So this was from a 2007 vintage Equinox fuel cell vehicle that General Motors built. It's a good indication. In the rear, you can see at the far rear, that thing sticking up is the receptacle. So that's where the hydrogen comes in from the fueling station. Those are 3 cylinders used to store the hydrogen. And then we have a thing called a rechargeable energy storage unit. The reason they say rechargeable energy storage is that can be an ultra cap, that can be a flywheel. It could be anything that you can store energy in. Then there's a DC to DC converter. That's power electronics. And what that does is it allows the battery to operate at the voltage it likes to, for the fuel cell stack to operate at the voltage it likes to, and it allows during regeneration for that current to flow back into the battery pack. Next slide, please. So this is a diagram courtesy of Toyota. I won't go into any great detail, but if you have some time, you can look at the different things. And one of the interesting things is you'll see that they've tried to eliminate various things in the system by using software, by using various techniques and maturing the systems. So we've had many, many years. I believe the first fuel cell vehicle that was built by General Motors was 1964, and that was using what was a Gemini fuel cell to power the vehicle. Next slide, please. So the first section of the training would be PPE and hydrogen safety. You can see some of the articles we use, like Nomex garments, balaclava to protect in case there's a fire. Interesting thing with fuel cell vehicles is the different types of PPE required depending on what function you're doing during the service process. So if you're working with the hydrogen, you need a Nomex garment. You know, if you're working with an inverter with the cover off, you're going to need an static garment and a wrist strap. So it's important that the technician realize what he's doing when and what kind of PPE he needs at that particular moment in the service process. One of the things you see here is a broom, and that's one of the properties of hydrogen is it not very visible, especially during daylight, and so it's hard to tell when it's burning. So what they do in refineries is they actually use a broom that they hold in front of them if they think there's a hydrogen leak or a possible fire. It's a real easy way to detect it. Next slide, please. So these are the sections under the Ppe and Hydrogen Safety. We would train in hydrogen PPE, hydrogen personal safety, hydrogen facility safety, because that goes hand in hand with the personal safety and everybody else that's working around that person that's working on the hydrogen vehicle. Then we also go into compressed gas safety. This section of it is very similar to what you would learn if you were taking a gas oxyacetylene welding course or something like that, just how to handle the cylinders, how to use regulators, how to store the bottles, all those types of functions. Next slide, please. So then we get to the hydrogen storage system. This is a quantum storage system, carbon fiber tanks. I believe this one was 350 bar. No, it says 700 MPa. So this was when we first switched from 350 bar standard to a 700 bar standard for hydrogen storage systems. You can see a lot of the different features of the tank system, and it is indeed a system. Next slide, please. So this is a compressed gas storage vessel, hydrogen specifically. It's a type 4. So as John sort of alluded to, there's type 1, which are just your standard aluminum or steel cylinders. There's type 2 and 3, which are metal cylinders that are reinforced. And then there's type 4. Type 4 is usually fully carbon fiber composite. The inner liner is polyethylene type material. It's a plastic, and the reason being is that hydrogen can get through just about anything, but these polymer materials are very good about keeping the hydrogen inside the pressure vessel itself. On the front of it to the left is what we call an on-tank valve, and we'll discuss that in just a second here. Next slide, please. These are some of the components you'll find in a hydrogen storage system. The on-tank valve, which usually has an electric solenoid that turns the hydrogen flow on and off. It will also usually have a manual override that lets you defuel a tank if the solenoid or other parts of the valve are damaged. It also allows the monitoring of the temperature inside the tank itself. There's pressure sensors, regulators, filters, pressure relief devices, and the receptacle. Receptacle is very similar to CNG, but its O&M, the outline and measurement design, is different so that you can only refuel that particular fuel on that vehicle. So the length and dimensions are such that you can't refuel a hydrogen vehicle with CNG or vice versa. You can't even refuel a 350 bar hydrogen powered vehicle with 700 bar if it has a 350 receptacle. Next slide, please. So under the hydrogen storage system, we're going to look at theory and operation of hydrogen storage systems, the schematics, pressure vessels themselves, and this ties into what John was talking about, being able to inspect pressure vessels. CNG and hydrogen vehicles both require periodic inspections, and if there's an issue, a lot of times it's good if you can remove the OTAV and look on the inside of the vessel to see if there's been any damage caused by over temperature, or sometimes if you reduce the pressure too quickly or too low, it can collapse the liner. Hydrogen storage system on tank valve and the pressure regulation and regulators. Next slide, Maddie, please. Maddie, hello. There we go. I'm lagging on my end. It's probably my computer. That's why we're having Maggie do the slides. I know it's a bit annoying, but my computer lags quite a bit. Pressure relief devices, high pressure fittings and connections. This again ties into what John was talking about. There are so many different types of high pressure fittings from different vendors, different suppliers. They're all usually unique to themselves, to their own company, because of patent requirements and regulations. So it's very important for technicians to understand how to identify those fittings, how to use them, how to properly inspect them, and how to make sure that they don't leak. There's high pressure leak detection systems and methods that need to be trained on. Inerting is a major thing to learn about hydrogen powered vehicles and their storage systems, is how to take a pressure vessel that's basically pure hydrogen and then inerted it with a inert gas down to less than 2%, so that when you do open it to the external world, it's non-flammable. ECM and software for hydrogen storage system, we'll go over that. And then fueling of hydrogen vehicles, both at a station and also standalone, like at a service facility. Next slide, please. We get to the fuel cell propulsion system. So this is an integrated fuel cell propulsion system that you would find in a front wheel drive vehicle. So it's very similar to an ICE front wheel drive vehicle. There is an electric motor, just like a BEV. You have the fuel cell stack, which is just sort of a boring box. You have a DC to DC converter, heat exchangers. Buried deep in this is also a inverter, which allows the DC to become AC to drive the electric motors. There's compressors, there's radiator modules, and all mounted on a subframe. Next slide, please. So the fuel cell stack system. This part of the training would cover basic fuel cell theory and operation, fuel cell system schematics, constant voltage monitoring, ECM and software for fuel cell systems, and fuel cell propulsion system overview. There's a lot of theory and operation. Generally, these types of training classes would be half in the classroom and half in a garage or laboratory with hands-on type experience. That's the best way to teach these. Learn it in the classroom and apply it in the garage type of scenario. The reason you need a lot of this information with fuel cell vehicles is the fact is we integrate components. It's not very easy to troubleshoot just by swapping out a component anymore. You really have to understand the operation of the vehicle and what's causing what and when what reacts to what, so that you can properly repair it and not just throw parts at things. Next slide, please. The next major subsystem is the anode subsystem. That basically takes everything from the hydrogen storage tank, which is at a high pressure. Generally, there's a regulator involved that'll drop that pressure down to maybe 2 atmospheres or so, and then bring it forward to the injectors, or however we're inserting the hydrogen into the fuel cell stack. And then that goes through a manifold of some sort that'll take the hydrogen gas and distribute it among all those cells in the fuel cell stack. Next slide, please. So there's various subcomponents, injectors. The injectors are unique in the fact that they require very, very precise dimensions on the inside of the injector, because the hydrogen can leak by just about anything. So they're very precise injectors. They're very similar to CNG, just a lot more lower tolerances as far as assembly. Control valves are very important because, as we discussed before, a fuel cell vehicle keeps running as long as it has hydrogen. One of the things that's discovered early on was that if you had a fuel cell and you allowed oxygen to leak back into the system, or hydrogen to leak up to the fuel cell, that even though you designed a fuel cell for 100,000 miles, even when it was just sitting there overnight, it was getting 8 hours of equivalent runtime, because it was getting oxygen and was able to keep operating at a very low voltage level. And that took away the life of some of the components. So that was a lesson that we learned early on. Hydrogen recirculation. So the hydrogen fuel cell system, PEM system, is a dead end system. So the hydrogen goes in, but it doesn't come out. On the cathode side, you get air coming in and it goes out the exhaust, but the hydrogen dead ends. So there's two things that happen. One, we have to recirculate that hydrogen back into the system by pressurizing it again. Two is we will have to get rid of water and also nitrogen on that can leak across the PEM membrane. Next slide, please. So in the anode subsystem, the students would learn anode subsystem mechanizations, hydrogen injection and metering, this hydrogen recirculation pump, which I talked about, that recompresses the hydrogen back into the system, nitrogen purging, liquid water removal, and anode outlet valve. Now, the liquid water removal, you don't want to dump hydrogen overboard, so it's critical that you have the ability to collect a little bit of the water and to drain it and the nitrogen, but not to lose any hydrogen, because that's going to, be dumping hydrogen in the atmosphere, which you don't want, and it also reduces your efficiencies. So there's a lot of software and thought that's gone into nitrogen purging and liquid water removal. Another thing about liquid water removal is when it freezes, it can create damage in the fuel cell stack. So one of the things the OEMs do is figure out how to not have any water liquid water in a system when they shut it down, in case they get to freezing temperatures at night. Next slide, please. We then go to the cathode subsystem, and that basically takes everything from the air intake through the mass flow sensor, through the air filtration system, through the compressor, et cetera, out through in through the stack, through the manifold system, and then out through the exhaust. Next slide, please. So various components, drain valves, air cleaners, charge air cooler. Think of a charge air cooler as an intercooler. When you're compressing atmospheric air, the temperature rises. Fuel cell stack doesn't like hot air, so we use generally a liquid-to-liquid intercooler that lowers the temperature of that incoming air after it goes through the compressor. Initially, we measure the mass flow. So just like on an ICE car, we're measuring the amount of air that goes into the system. So there is no throttle body or anything like that on a fuel cell stack. You basically control the operation of the fuel cell by measuring the amount of air that's coming in, and also by the amount of hydrogen you're injecting into the fuel cell stack. Next slide, please. So a bunch of sections on the cathode subsystem. The mass airflow sensor is very similar to a high performance gasoline engine, compressors and turbo machines, charge air cooler, air flow valves, again, valves that are very critical and usually designed to a fairly high tolerance. The exhaust system, sort of interesting, the exhaust system in a fuel cell vehicle, because it's such low temperature, you can basically use radiator hoses as the exhaust system for a fuel cell, which is really good because the moisture content in the exhaust of a fuel cell vehicle is quite high, so it tends to attack various metals unless you have like stainless or something like that. So rubber is actually a very, very good exhaust system material. You have pressure and temperature and humidity sensors and a humidification unit that takes water out of the exhaust and puts it back into the cathode airstream. We need to keep that PEM membrane moisturized, so it requires a certain amount. You don't want liquid water, but you want a high moisture content for the maximum efficiency of that PEM membrane. Next slide, please. So then we get to the cooling system. A lot of manufacturers use a high voltage current coolant pump because, like I said, most of the waste heat for a fuel cell comes out through the radiators and heat exchangers. We need a low conductivity coolant, but in addition to that, we need no particulates in that coolant because of the small passages that we find in the fuel cell itself. Even nowadays, battery BEVs are using liquid cooling, and they also have the same type of situation where they don't want you to accidentally plug off some really small passages. So they're basically coalescing around coolant filters. One of the other things that we also see in the coolant system is an ion exchange module. And what that does is it keeps the resistivity or low conductivity of the coolant. Reason being is if you have a high voltage coolant, basically at the fuel cell stack, it's right next to the high voltage. You don't want that getting into the outside world. So low conductivity keeps the fuel cell stack isolated from the rest of the world. High voltage coolant fans, we used to joke at General Motors that was part of the propulsion system because at the time our coolant fan was actually 2 kilowatts. So it's a very powerful fan there again, because we're dropping most of our waste heat out of through the heat exchanger and not the exhaust. Next slide, please. So in the cooling system, we're going to be looking at cooling system theory and operation, pumps, bypass and controls, coolant heater. Coolant heater is critical because it allows the stack to get to operating temperatures quicker, and it also allows for cabin heating if you need it during startup. Coolant and coolant reservoir, ion exchange we talked about, and the heat exchangers and fans. Next slide, please. Then we get to the fuel cell high voltage schematic. You can see here it's very similar to a BEV. If you just take the bottom half of it, you have a battery electric vehicle. You add the fuel cell and its hydrogen tank, and another, usually the DC to DCs are integrated, they're not unique. And then we get the inverter DC to AC and drive an electric motor through a single speed gearbox. Next slide, please. Because this program was designed to be integrated with the other earlier presentations, the amount of high voltage training we do would just be limited to what is specific for a fuel cell vehicle and the components that are on a fuel cell vehicle that are unique to that type of vehicle. Next slide, please. So as far as specialized equipment, not a lot required that if you're already working on EVs. Obviously the bottled gas regulators, hoses and refueling nozzles, an event stack, and leak detection for the hydrogen, and a differential gas flow measurement equipment if you're going to try to diagnose whether a fuel cell stack is good or bad. Next slide, please. Just the next 2 slides are codes and standards that are applicable to either a vehicle, hydrogen-powered vehicle, or a building where you're working on it, or parking it, or a refueling station. Next slide. And then the next slide after this, please. So this shows a representation of Honda and how they defuel their vehicles outside. Early on, dealerships did not have the ability, or it wasn't worth their time to really dedicate a structure to working on hydrogen-powered vehicles. So they would want to defuel the vehicle outside, and this just illustrates that you need a certain amount of area and a vent stack to be able to do that safely. Next slide. So these are some of the features you would find in a hydrogen safe building. You'd have hydrogen detectors that are on the left up at the ceiling, obviously, because hydrogen rises. You have on the right various types of vent stacks that would be required to vent any hydrogen outside of the building if you're defueling inside. Interesting solution is this one in the center here. It's actually a service bay for any combustible gas type of vehicle. And so you can actually place this in your normal service building and have it hydrogen safe, but not have to dedicate the whole building to it. Next slide, please. So some of the special building structure requirements to service a fuel cell vehicle, obviously a facility with hydrogen detection, or in California, we're lucky enough that some of the dealerships have open outdoor service areas, so they don't require the hydrogen detection. Flammable and non-flammable compressed gas storage, very similar to if you have oxyacetylene torches on site, same type of storage. Permanent vent stack or portable vent stack like we talked about, and enough exterior space to comply with fire code setback requirements. Next slide. So this fuel cell vehicle service certification, this course of study was designed to be added into the previously described EV certifications as an add-on. It could be modified if all you're interested in is fuel cell vehicles. It can be modified to be a standalone certification without prerequisites, as long as we're using the specific modules from the EV certification program. The program has a more extended time frame, as Ken mentioned, that it's not near term like the other programs are for light duty vehicles. It is applicable to just about any type of PEM fuel cell vehicle maintenance, whether it be a bus, truck, forklift, light duty vehicle, heavy duty truck, airplane, UUV. General Motors worked with the U.S. Navy on unmanned underwater vehicles that were powered by fuel cells. So next slide.
Well, Tim, let me chime in here and thank you very much. I think everybody needs to have this recording. If a program was attempting to start a fuel cell program at their respective college, this would be a great starting point to present to their advisory, to their college. So thank you for doing that. I've got a few questions if you're ready. There was one question here, and this is and it disappeared. So I'm going to ask it as best as I can. So as the transit companies have been using electric, natural gas, compressed natural gas, and introducing fuel cell transit systems such as Sunline, what are the advantage of bringing fuel cell to replace electric or compressed natural gas buses?
Yeah, generally it's fast fueling time. I know Sunland in the past has used, in their CNG buses, actually used what they call high-thane, which is hydrogen with CNG to get them more energy in a particular volume of gas. So they were able to use both the high-thane CNG and hydrogen to power buses. The quick fueling times is critical. The zero emission, obviously, CNG isn't zero emission. That's critical because you bring buses, they come through, a lot of them are operating, 20 hours a day or 18 hours a day. So you want something that will fuel fairly quickly, even if the high capacity chargers, battery chargers, if it's a long route or something like that, it's better to have a fuel cell vehicle than a battery electric because of the charge times and utilization. Same with semi trucks.
Another question is real straightforward. Service life of a fuel cell stack.
I don't know that because I'm not currently employed by an OEM. I know the standards were well over 100,000 miles. That's what I was alluding to, is the fact that we had designed stacks for 50 or 100,000 miles, and they were being used up fairly quickly, and we couldn't figure out why. And that was because the oxygen was sneaking into the fuel cell stack, so it was running 24 hours a day, or until it used up the hydrogen that was there. So we were actually found that we were using up a life of the vehicle when we were parked. So that was a critical finding along the way. But yeah, 100,000 miles is the minimum. I imagine it's a piece of plastic, so you always have a trade-off with PEM fuel cells, how thick the membrane is versus how efficient the fuel cell stack is. So the thicker the membrane, the less efficient it's going to be, but the more reliable it's going to be. So those are always trade-offs. Also, monitoring pressures. You want to always keep the anode and cathode sides at the same pressures to avoid stress on the membranes. And that's in controls and functions and valves and things that help us maintain that.
There's a question about arc flash potential of a fuel cell vehicle.
Arc flash, as far as I guess I'm not quite clear.
And I don't know either. That's the question. What is the arc flash potential?
Yeah, it's the same as any electric vehicle. DCs, you're generally, they're isolated. So within the stack, no. External, it'd be just like a battery electric vehicle. So if you drop a wrench across, potentially across two positive and negative, yes, you can get the arc flash.
So I think a follow-up on that is the question had to do with more multiple infrastructures needed for battery electric buses and fuel cells. That was the first question.
Okay.
Do you see any need for agencies to have both fuel cell buses and electric buses?
It depends on their routes. It's an application. My last job, we always used to say there's no silver bullet, whether it's synthetic fuel or battery electrics or fuel cells, or each one has its own pluses and minuses. It just depends on what kind of routes they run and their intent. Cost obviously is one. So there's no magic answer. Each agency really has to look at what their needs are and go from there.
Had a comment about broomsticks, and in the Navy, broomsticks are used as well in steam, high pressure steam, and fire rooms, engine rooms. Navy guys are familiar with this, so it could cut the broomstick in half depending on where you're working. But I know, being on a carrier myself, it was a dangerous environment as you're working with high pressure steam.
Yep. Yeah, so with hydrogen fuel cell vehicles, you not only have the chance for fire, you also have the chance for high pressure gases. But generally, those are limited to inside the cylinders. Once they leave the cylinders, the pressure is dropped down before it even leaves the vessel.
A lot of us are not familiar with fuel cell systems, and getting into this, it's a little bit daunting. I've looked inside of fuel cell cabinets of stationary fuel cell systems. It looks pretty daunting. But servicing these systems, how much attention or service is needed to keep a vehicle at maximum operating conditions?
Very little service. It's basically an electric vehicle. So other than it has a few more moving parts. Obviously, it has pumps and compressors and injectors, but it pretty much has the reliability of a battery electric vehicle. One of the things you'll see is that one of the uses for fuel cells right now is backup power for like cell phone towers and things like that. So those are systems that are going to be sitting there off for weeks, months at a time, and then be required to power up in minutes or seconds to supply the power. So they can stand alone for a long time. That's one of the reasons the Navy was interested in fuel cells, is the fact that it wasn't going to go dead. You know, if we used a BEV for powering a underwater vehicle for long periods of time, and it just sat there, then eventually the battery would discharge. Whereas a hydrogen-powered fuel cell could sit there for a long, long period of time, and the fuel would still be in the fuel tank, and it could operate with 0 emissions.
I'm going to read this question, and you may want to pass it to Mark, but would this training be considered mandatory for Society of Automotive Engineers certification or as preparation for an SAE test?
That I'm going to pass off to Mark.
Okay. Okay.
Okay, Ken, could you read that one more time? Just
Sure.
one more time.
Would this training be considered mandatory for a Society of Automotive Engineers certification or as preparation for an SAE test?
I'm trying to rack in my head here what an SAE certification is and an SAE test.
Okay. Well, we're promoting vehicle electrification, level 1 vehicle electrification
Right.
certification.
Yep.
And the second, level 2, and the third, level 3, are all in process. So right now, as we're talking about fuel cell, we are not moving quickly towards fuel cell. And I'd like to address that between you, Mark, and Tim. You know, we're at kind of an interesting place. Maybe we were here 12 years ago with vehicle electrification or beyond, when we were saying that electric vehicles were not going to really be the dominant vehicle on the road at any time. Now we're here on another rendition of fuel cell. How do we train people, and how aggressively should we be training people to get into this next level of industry?
Is that to me, Ken?
Both of you.
Okay. Okay. Well,
you may have different answers.
Yeah, sure. Well, from the electric side, you know, we're doing that today. You know, unfortunately, over the last, we'll just call it since the year 2000, when hybrids came in, we really didn't have a real good block of you know, training standards that were being used. I mean, everybody kind of had their own way they were doing it. The OEMs all kind of had their own twist on it, but it really didn't get down to the core technologies. That's one of the issues that we had. So what happened was we marketed vehicles, and we marketed them to, you know, everybody. And then what we did is we had the cars marketed, they went out in the field, but there had not been any real core training yet that had been rolled out. The OEMs had their training, don't get me wrong, but that's not real core training. That's just, you're training to a product, and that's fine, but you're not training to a technology. And we completely missed that whole thing. We completely missed it. There was no core technology training. Really, the only guys who had any type of core training were the engineers that were putting it together. Outside of that, there really wasn't any, and we completely missed that. So now we're kind of circling back around, and we're going through now what you would normally go through an internal combustion engine program. You know, you have to learn engines, pistons, crankshafts, camshafts. You have to learn fuel systems. You have to learn ignition systems. We didn't do that with electrics. We just, you know, they kind of got marketed, and the core stuff never really got embedded. We had plenty of product information, but not technology information. So now that's where we're at with the certifications here. Is we're going to the core rather than trying to teach a product. We're going to the core technology. So so that's necessary because we don't have it yet. It hasn't really been implemented yet. I know a lot of people have tried, but it's not really there. You know, it's something that got missed, and I'm not sure why it got missed or how it got missed, but it did. And so I look at what Tim had, and I'm not going to speak for Tim, but I look at what Tim has, and it's going to have to go through the same thing where we're going to have to learn we should be learning the background on it first before we learn product. That way it won't matter what product you're on. You'll know the background on it. So it doesn't matter whether you're on a Ballard system or GM system or Honda system or whoever it is, you got enough background in it because you've received some core technology training and you've gotten that, so you'll be able to apply it. And that's what's missed. And that's why the certification training is so important, is because it gets into the core technology. So anyway, that's my answer to it.
Okay, thank you, Mark. And Tim, you want to add to that?
Yeah, I agree with Mark in the fact that if you have the basics and general information, then a service manual is all you really need to work on any vehicle. You know, the service manuals are written in such a way that they're designed to be used by somebody that has the basic knowledge, basic tools, whatever that might be for that particular vehicle.
Hey,
Okay.
Ken, this is John.
Hey, John.
Hey, the same thing happened, what Mark was talking about, when NFPA came out with their NFPA 2. We had a real hard surge at first getting this document together, and then the committee went stagnant for almost 3 years. And it isn't until the last few months, that the committee has started forming itself to come back together to review the standards that they started putting together 4 or 5 years ago. So as Mark had implicated there, that the push was out there, but the follow through wasn't there. And this is what's happening to a lot of the fleets and the repair facilities, is the product shows up and nobody has the specific product, or they only have the product training, but not the background piece to it. And as Mark was alluding to, that if you have that background piece, you could virtually pull or approach any vehicle and have a good understanding of that technology. For some reason, it just got missed or dropped or set on the shelf. I'm not really sure myself, but the same thing happened on that as has happened to CNG and some of the other fuels like biofuels.
Well, we are at a challenging time. We're at the right time, and we have a lot of work to do right now. Thank you, Tim, for that presentation. That was great. Thank you.
Thank you for listening. Appreciate everybody online.
I'm going to introduce Dr. Mark Horton. I'm going to be real brief here, but I love this paragraph that I'm going to read about. Go ahead and thank you, Maddie. Dr. Quarto's passion for educating and training the next generation of automotive technicians and engineers has connected him with many international educational projects. Dr. Quarto provides instruction of hybrid, electric, and plug-in vehicle systems for the SAE, the OEMs, Tier 1 suppliers, and in the college environment. He is a patent holder for electric drive systems, testing tools, and battery testing processes. Dr. Quarto holds a doctorate in technical education and hybrid systems from Nova Southeastern University, master's degree in electric machine technical education, and bachelor's degrees in electrical engineering and automotive technology. Mark, welcome, and thank you for being pivotal for all of these webinars for technicians tuning in, and more to come.
Well, thank you, Ken. I appreciate the work that we've done thus far, and also working with Tim on the fuel cell standards. It's been a pleasure. I have a background with Tim. He and I go back quite a ways, and it's always a pleasure to work with him, and it's been a pleasure working with you on this. And so I've got I'm going to be sharing my screen here, Ken. So if we're ready to do that.
Okay.
Okay, so let me grab my screen share, and that should be up. Okay, we good, Ken?
Yes, I think I'm looking for the screen. It says you're sharing, but I'm not seeing it quite yet. There it is. Yay.
Okay, we got a little bit of a delay. Okay. All right, so mine's going to be very, very short today. What I'd like to do is provide just a real quick status for the EV Pro Plus L1 certification update, and then how it would apply to what Tim just went through. How would knit this info, the L1 info, especially because that's high voltage safety and safety systems, into the fuel cell certification. So it's kind of a cross-pollination. So if you take a look at where we're at for status, we have our first pilot class coming up at Cerritos College. This is in July. We have a second pilot at Ferris State in August, and then we have a third pilot at Sunline Transit in Southern California. So the pilots are there to just kind of get us to the point we can hammer this out, even though it's going to be train the trainer type of thing, but we're really going to be just hammering things out. We expect there to be some rough edges on the first one, fewer rough edges on the second one, and by the time we get to the third one, we should be pretty good on where we're at for the program as it goes out the door as a final product. So I'm looking forward to that, to get the L1 off and running. I will say that there's going to be a lot of rigor to it, and I'm hoping that those that are going to be attending the classes from here on out for the L1 are going to be prepared for the rigor. This is going to be a certification that you're really going to have to earn, and it's going to be a hands-on and written, and it's going to be getting into some of the finer points of electrification, and so just be prepared to really put the nose to the ground, because there's going to be a lot to it. All right, the other thing I wanted to go through is just to again reiterate that the L1 program would also provide some springboarding for the fuel cell program. So of course, as Tim has already stated, there's the high voltage side of the fuel cell system as well as the hydrogen side. And so there's likely going to be quite a few elements of the L1 certification that are going to port over to the fuel cell. Of course, we'll figure that out as we go, but this may lead us to the point where if somebody takes the L1 certification, that's a safety part of it, that would comprise enough for somebody to qualify in the fuel cell area. Now, I know that there's going to be some fuel cell specific things that are going to have to be addressed, but at least if you get the L1, you'd be able to branch off and go into the electrified vehicle area or over to the fuel cell area. And maybe what we could do is, and this would be more Tim than me, but get into the fuel cell area where there's only got to be specific things that need to be hit because someone would have already had the L1. So, so the L1 will likely be pretty mature by the time the fuel cell certification is implemented. So that's another good thing about the L1 is that it will be mature, and that way we'll have all the everything will be wrung out of it by then. So we'll kind of know what we've got. And then fuel cell is also going to have some elements of the level 2 and level 3 certifications, because the level 2 and level 3 certifications are going to involve things like battery packs, electric machines, DC to DCs, power inverters, and things like that. A lot of that's going to cross-pollinate to fuel cell. So again, as we go forward with what we currently have in levels 1, 2, and 3 on the plug-ins, hybrids, and BEV vehicles, we can see how much of that cross-pollinates over to fuel cell to see what exactly we would need to do to completely knit that together. So I think there'll be quite a bit that will cross-pollinate. Obviously, the fuel cell side of it is going to be completely new. Anytime you get into the stack, any of the systems that support the stack, and then the hydrogen piece of it, are all going to be very different. But I think there's some things from the electric vehicle side that can be used on the fuel cell side. So I think there's some benefit to leveraging that. If you want more information about the certifications, again, for the electrified vehicle part, you can get a hold of Chris Quarto. There's her direct phone number. And then if you want to go just get through email, you want to get more information, you can go at info@evproplus.com. And that's where you can request more info, or if you just want to make a direct call, you can do that. So my information has not changed for the last four or five times. I can't remember now. I've been on here. So my information hasn't changed. So anybody can contact me at any time. So Ken, with that, I will throw it back over to you.
Thank you, Mark. That was great to conclude this 5-part series today. Appreciate, again, Mark, Tim and John today, and especially we want to thank Maddie, who's back there making sure we're all in order and things have lined up, and appreciate all of Clean Cities who have sponsored this, and the Mobilize California. Great stuff, and looking forward to the Train the Trainer series that are coming up here in the next few months. No other questions, guys, so we're going to sign off.
Thanks, everyone.